Welcome to this walkthrough of LeetCode problem number 1088, confusing number 2. In this session, we'll explore the problem, break it down step by step, and discuss different approaches to solve it. Let's dive in. In this problem, we are dealing with a concept called a confusing number. A number is considered confusing if, after being rotated 180 degrees, it transforms into a different number, and all of its digits remain valid under this rotation. Now, what are these valid digits? They include 0, 1, 6, 8, and 9. When rotated, 6 transforms into 9 and vice versa, while 0, 1, and 8 remain unchanged. On the other hand, digits like 2, 3, 4, 5, and 7 are not valid, meaning that any number containing these digits cannot be a confusing number. The goal of the problem is to determine the total count of confusing numbers within the range from 1 to a given integer n. This means we need to identify all numbers in this range that meet these criteria and return their count. The output for this problem is an integer that represents the number of confusing numbers between 1 and n, inclusive. Let's look at an example to clarify. If n equals 20, the confusing numbers in this range are 6, 9, 10, 16, 18, and 19. For instance, the number 6 transforms into 9 when rotated, and since the result is different from the original number, it qualifies as confusing. Similarly, 9 becomes 6 when rotated, which also meets the criteria for being confusing. Looking further at the example, the number 10 rotates to form 0, 1, which is essentially 1, a different number, so it's confusing as well. Then we have 16, which rotates to 91, 18 to 81, and 19 to 61. All these results are different from their original numbers, making them valid confusing numbers. Now, let's consider a second example where n is increased to 100. In this case, there are 19 confusing numbers in total. These include the 6 numbers we just discussed, as well as some additional numbers like 60, 61, and 66. Continuing with the example where n equals 100, the complete list of confusing numbers is as follows: 6, 9, 10, 16, 18, 19, 60, 61, 66, 68, 69, 80, 81, 86, 89, 90, 91, 98, and 99. Each of these numbers, when rotated, results in a valid number that is different from the original. Finally, let's examine a simpler case where n equals 1. Here, there are no confusing numbers because the number 1 remains the same when rotated, and therefore does not meet the criteria for being confusing. When solving this problem, there are several edge cases to consider. For the smallest possible input, when n equals 1, there are no confusing numbers. Another important case is when n consists entirely of valid digits like 0, 1, 6, 8, and 9. In such scenarios, we need to check if the rotated numbers are different from the originals to determine if they are confusing. Furthermore, if n contains a mix of valid and invalid digits, numbers with invalid digits must be excluded from consideration. Lastly, we must ensure that our solution is efficient and performs well even for the largest input, where n equals 10⁻⁹. This is critical to handle the problem's constraints effectively. To solve the problem of finding confusing numbers up to n, we start by considering two approaches. The first is the brute force method. The intuition here is straightforward. We iterate through all numbers from 1 to n and check each one to see if it qualifies as a confusing number. For this, we need to verify two things. First, that all the digits in a number can be rotated, meaning they belong to the valid set of digits, 0, 1, 6, 8, and 9. Second, we rotate the number by replacing each digit with its rotational counterpart, like turning 6 into 9 or 9 into 6, and then compare the rotated number with the original. If the two are different, the number is confusing. However, this approach has a major downside: its complexity is n*d, where n is the upper limit and d represents the number of digits. For large values of n, this becomes highly inefficient because we end up performing repetitive computations and revisiting the same subproblems unnecessarily. To address these inefficiencies, we can turn to a more optimized approach using depth-first search, or DFS. Here, instead of iterating through all numbers, we generate valid numbers recursively. Starting with a single valid digit, we build numbers step by step by appending more valid digits, checking at each stage whether a number is confusing. If the number exceeds n, we stop the recursion. This avoids processing invalid numbers entirely and significantly reduces redundant computations. The DFS-based approach improves efficiency by leveraging the small set of valid digits, 0, 1, 6, 8, and 9. Instead of iterating through every number from 1 to n, we focus only on those that can actually be confusing. By pruning invalid paths early in the recursion, we avoid unnecessary checks and computations. This makes the approach much faster than brute force, with a complexity of 5 to the power of d, where d is the number of digits in n. This is a substantial improvement, especially for larger values of n. Now, there are a few key observations that drive this strategy. First, only the digits 0, 1, 6, 8, and 9 can form valid rotated numbers. Any number containing digits like 2, 3, 4, 5, or 7 can be ignored outright, as these digits are not valid for rotation. Second, to be considered confusing, a number must differ from its rotated counterpart. For example, numbers like 181 or 69, which appear the same when rotated, are not confusing. Finally, the DFS approach directly generates valid numbers instead of filtering through invalid ones, making it both efficient and clean. This is why we've chosen the DFS-based strategy. It effectively reduces the search space by leveraging the small set of valid digits and avoids unnecessary iterations, making it scalable for larger inputs. When comparing strategies, each has its own trade-offs. The brute force approach is simple to implement, making it easy to understand and apply. However, it's not efficient for large values of n due to its exhaustive nature, as it involves iterating through all numbers and performing repeated checks. On the other hand, the DFS approach is slightly more complex to implement but offers significant efficiency gains. It avoids redundant computations, focuses only on valid candidates, and prunes invalid paths early in the process. Additionally, while an alternative breadth-first search, or BFS, approach could be used, it has a similar computational complexity to DFS and doesn't provide any distinct advantages in this specific problem. Overall, the DFS approach strikes the best balance between efficiency and clarity. By focusing on generating valid candidates and reducing unnecessary checks, it addresses the inefficiencies of brute force and provides a scalable solution for finding confusing numbers. This makes it the ideal strategy for solving this problem. To solve the problem, we first need to understand what makes a number confusing. A number is considered confusing if, when rotated 180 degrees, it transforms into a valid number that is different from the original. For instance, the number 89 becomes 68 when flipped, so it qualifies as a confusing number. However, a number like 11 remains unchanged when rotated and is therefore not confusing. To approach this, the first step is to identify the digits that remain meaningful when rotated. The valid digits are 0, 1, 6, 8, and 9. These digits map to specific rotated counterparts. 0 maps to 0, 1 maps to 1, 6 maps to 9, 8 maps to 8, and 9 maps to 6. Any number that contains digits outside of this set, such as 2 or 5, is immediately invalid and cannot be a confusing number. This foundational understanding allows us to proceed with the next steps of the algorithm. Now that we know which digits are valid, the next step is to reverse and rotate the digits of a number. To do this, we extract each digit one by one using modulo and integer division. As we process each digit, we first check if it is valid. If an invalid digit is encountered, we can stop immediately because the number cannot be confusing. If the digit is valid, we append its rotated counterpart to construct a new number in reverse order. Once the rotated number is fully constructed, we compare it to the original number. If the rotated number matches the original, the number is not confusing. However, if the two are different, the number qualifies as confusing. To find all confusing numbers up to a given limit n, we repeat this process for every number in the range from 1 to n. As we identify confusing numbers, we keep account of how many we find. The algorithm can be implemented efficiently using a few straightforward steps. First, we define a dictionary, rotation_map, to store the mappings of valid digits to their rotated counterparts. This allows for constant time lookups. Next, we initialize a counter to track the total number of confusing numbers. We then iterate through all integers from 1 to n. For each number, we extract its digits, validate them, and construct the rotated number using the mappings. After constructing the rotated number, we compare it to the original. If the two numbers are different, we increment the counter, as the number is confusing. Finally, after processing the entire range, we return the counter as the total count of confusing numbers. This structured approach ensures that we systematically check every number while keeping the implementation efficient. There are several key insights that simplify this problem. First, the validation of digits is critical, as only a small subset of digits is valid for rotation. If a number contains any invalid digit, it can be skipped immediately, saving computational effort. Second, constructing the rotated number in reverse order naturally accounts for how the digits appear when flipped. This eliminates the need for complex transformations. Third, an early exit strategy where we stop processing as soon as an invalid digit is found further optimizes performance. Additionally, edge cases must be handled carefully. For example, single-digit numbers are confusing only if they are 6 or 9, while numbers containing invalid digits, such as 2, 3, or 7, are skipped entirely. The algorithm relies on simple data structures and operations, a dictionary for constant-time digit mapping, basic integer arithmetic for digit extraction, and a counter variable for tracking results. In terms of complexity, the time complexity is O, n*d, where n is the range of numbers and d is the average number of digits per number, as we process each digit individually. The space complexity is O(1), because we use only a few variables and a fixed-size dictionary, making this approach highly efficient. The code defines a solution to the problem of finding all confusing numbers up to a given number n. A confusing number is a number that, when rotated 180 degrees, becomes a valid but different number. The solution starts by defining valid digits that can be rotated 0, 1, 6, 8, 9, and their mappings to their rotated counterparts. For example, 6 becomes 9, and 9 becomes 6. The is_confusing function checks whether a given number is a confusing number. It reverses the number while applying the rotation mapping, and then compares the rotated number to the original. If they are different, the number is confusing. The DFS, depth first search, function is used to generate numbers recursively, starting from 0. It appends valid digits to the current number, ensuring that we explore all possibilities. If the resulting number exceeds n, we stop exploring further. Additionally, we skip numbers that start with a leading 0. For each number generated, the DFS function checks whether it is confusing using is_confusing, and if so, increments the count. This count is then accumulated across recursive calls. Finally, the DFS function is called with the initial value of 0, and the total count of confusing numbers up to n is returned as the result. This approach ensures that all valid numbers are considered, and only those that are confusing are counted. Here, we start with the Java implementation for solving the confusing number 2 problem. First, we define a constant map, valid_digits, which maps specific digits to their rotated counterparts. For example, 6 maps to 9, and 9 maps to 6, while digits like 0, 1, and 8 remain the same when rotated. This map helps us identify which digits are valid for creating confusing numbers. Next, we define the main method, confusingNumberII, which takes an integer n as input and returns the total count of confusing numbers up to n. This method calls a recursive helper function, DFS, which performs a depth-first search to explore all possible numbers generated using the valid digits. Inside DFS, we first check if the current number exceeds n. If it does, we return 0, as it's outside the valid range. Otherwise, we initialize a count variable and check if the current number is confusing using the isConfusing method. If it is, we increment the count. Then, we iterate through each valid digit and calculate the next number by appending the digit to the current number. To prevent leading zeros, we ensure that the next number is greater than 0 before making a recursive DFS call. Finally, we return the total count of confusing numbers found so far. To determine if a number is confusing, we use the isConfusing method. The method takes a number as input and begins by storing its original value. We also initialize a variable, rotated, to store the rotated version of the number as we compute it. While the number is greater than 0, we extract its last digit using the modulo operation. If the digit is not in the valid_digits map, the method immediately returns false, as it means the number contains an invalid digit. Otherwise, we use the valid underscore digits map to find the rotated counterpart of the digit and append it to the rotated number. We then divide number by 10 to continue processing the next digit. Once all digits have been processed, we compare the rotated number to the original. If they are not equal, the number is confusing, so we return true. Otherwise, we return false. This method ensures that we can accurately identify whether a number changes to a different value when rotated, which is the key criterion for being classified as a confusing number. To solve the problem, we start by defining the valid digits that can be used to construct rotated numbers. These are 0, 1, 6, 8, and 9, and each digit has a specific mapping when rotated. For example, 6 maps to 9 and 9 maps to 6, while 0, 1, and 8 remain unchanged. This mapping is critical because it helps us determine if a number can be transformed into a valid rotated number. Next, we use a depth-first search, or DFS, approach to systematically generate all numbers up to n. The DFS begins with current equals 0, and from there, it explores all possible numbers by appending one valid digit at a time. For instance, when starting with current equals 0, we calculate the next number by multiplying current by 10 and adding a valid digit. For digit equals 0, the resulting number is skipped to avoid leading zeros. However, for digit equals 1, the next number becomes 1, and we proceed by recursively calling the DFS function on 1. Now, we check whether the number 1 is a confusing number. The is_confusing function compares the original number with its rotated version. For 1, the rotated result is also 1, meaning that the number looks the same even after rotation. Therefore, 1 is not a confusing number, and we return to the DFS process. Next, we explore other numbers generated during DFS. For current equals 6, the rotated result is 9, which is different from the original. This makes 6 a confusing number, so we increment the count. Similarly, for current equals 8, the rotated result is 8, which matches the original, so 8 is not a confusing number. Finally, for current equals 9, the rotated result is 6, making 9 a confusing number. After completing the DFS for all valid digits up to n equals 10, we find that the confusing numbers are 6 and 9. Thus, the output for this input is 2. In the next example, we increase the input to n equals 20. Once again, we start the DFS with current equals 0 and generate numbers by appending valid digits. As the DFS explores numbers, we check each one to determine whether it is confusing. For instance, when exploring current equals 16, the rotated result is 91, which is different from the original. This makes 16 a confusing number, so we increment the count. Similarly, for current equals 19, the rotated result is 61, which also differs from the original, so 19 is another confusing number. After completing the DFS, the confusing numbers up to n equals 20 are 6, 9, 16, and 19. This gives us a total of 4 confusing numbers, so the output for this input is 4. Finally, let's consider the case where n equals 5. Starting the DFS with current equals 0, we again generate numbers using the valid digits. However, as we explore, we find that most numbers in this range are either invalid or exceed the input limit. For instance, appending digits like 6, 8, or 9 results in numbers greater than 5, so these are skipped. For current equals 1, the is_confusing function finds that the rotated result is also 1, meaning it is not a confusing number. Since no other numbers within the range satisfy the criteria, the count of confusing numbers is 0. Therefore, the output in this case is 0. In this problem, we are tasked with finding all confusing numbers less than or equal to a given input, n. To solve this efficiently, we use depth-first search, or DFS, to systematically explore all valid numbers that can be formed using the digits 0, 1, 6, 8, and 9. Each node in our DFS tree represents a number created by appending one of these valid digits to the current number. The depth of the tree is limited by the number of digits in n, which is at most log base 10 of n. At each depth, there are up to 5 branches, one for each of the valid digits. This gives us a maximum of 5 to the power of k nodes in the tree, where k equals log base 10 of n. Additionally, for each number generated, we need to check if it qualifies as a confusing number. This involves reversing the number and comparing it to the original, which takes time proportional to the number of digits, or O of log base 10 of n. Together, these factors determine the computational effort needed for our solution. Now, let's calculate the total time complexity based on our analysis. The DFS explores up to 5 raised to the power of log base 10 of n nodes. For each of these nodes, we perform a confusing number check, which takes O of log base 10 of n time. Multiplying these together, the total time complexity becomes O of 5 raised to the power of log base 10 of n times log base 10 of n. Using properties of logarithms, we simplify this further to O of n raised to the power of log base 10 of 5 times log of n. Since log base 10 of 5 is approximately 0.69897, this gives us a more concrete understanding of the growth rate. On the space complexity side, the main contributor is the recursion depth of our DFS. The maximum recursion depth corresponds to the number of digits in n, which is O of log base 10 of n. Additionally, we use a constant amount of memory for auxiliary variables like the list of valid digits and temporary variables for rotation. Thus, the space usage is relatively minimal. When we sum everything up, the total space complexity is primarily determined by the recursive call stack, which is O of log base 10 of n, or simply O of log of n. Let's also compare the DFS-based solution to a brute force approach. In a brute force solution, we would iterate through every number from 1 to n, checking if each number is confusing. This would take O of n times log base 10 of n time, due to the confusing number check for each iteration. The space complexity for brute force, however, is O of 1, as it doesn't use recursion. By contrast, the optimized DFS approach is much faster for large n, as it avoids unnecessary checks by pruning invalid branches early. Its time complexity is O of n raised to the power of log base 10 of 5 times log of n, which grows significantly slower than the brute force O of n log n. The space complexity, while slightly higher at O of log n, is still very manageable given the performance improvements. In terms of best and worst case scenarios, the time complexity remains consistent. The best case occurs when DFS can prune branches immediately upon finding numbers that exceed n, but since pruning doesn't drastically reduce the number of valid nodes to explore, the overall complexity remains O of n raised to the power of log base 10 of 5 times log of n. In the worst case, all possible numbers formed by the digits 0, 1, 6, 8, and 9 are valid in less than or equal to n, meaning the DFS has to explore every branch. Still, the complexity does not worsen beyond O of n raised to the power of log base 10 of 5 times log of n. This consistency highlights the efficiency of the DFS-based approach. Ultimately, the algorithm's ability to prune invalid branches and focus only on valid numbers makes it significantly faster than brute force while maintaining a space complexity that scales well even for large inputs. This makes the solution both practical and efficient for real-world use cases. When working with confusing numbers, there are a few common mistakes to watch out for. First, it's important to correctly identify valid digits. Confusing numbers can only include the digits 0, 1, 6, 8, and 9 because these are the only ones that either remain the same or rotate into a valid digit. For example, digits like 2, 4, 5, 7, or 9 are invalid because they don't produce valid rotations. 2, for instance, doesn't map to any digit at all. To address this, make sure your logic explicitly filters out these invalid digits. Another frequent issue is reversing numbers without applying the correct rotations. For example, reversing the number 69 foot gives 96, but you also need to swap 6 with 9 and vice versa during the process. Without properly mapping these rotations, the results will be incorrect. Finally, don't forget about edge cases like single-digit numbers or those that remain the same after rotation, such as 0, 1, or 8. These numbers are valid in rotation but do not qualify as confusing because they look identical before and after rotation. Including explicit checks for these cases will ensure your solution is robust. Another challenge is inefficiency caused by brute force implementations. If you attempt to iterate through all numbers up to n without eliminating invalid branches early, your solution will perform unnecessary computations, especially for larger values of n. A more efficient approach is to generate valid confusing numbers digit by digit, using only the valid digits. This strategy drastically reduces the search space and avoids wasting time on invalid numbers. Additionally, in languages like Java or C++, you need to be cautious about integer overflow when working with large values of n. Iterating through large numbers without considering data type limits can lead to errors. To prevent this, use data types that can handle large values safely, such as long or big integer. By combining efficient generation techniques with proper type handling, you can ensure your solution is both performant and accurate. When solving this problem in an interview setting, it's helpful to focus on a few key insights. Confusing numbers are defined by their ability to rotate into valid but different numbers. For example, the digit 6 rotates into 9, and 9 rotates into 6, resulting in a number that looks different when reversed. To solve the problem efficiently, avoid brute force and instead use a digit-by-digit construction approach. This method involves generating numbers recursively using only the valid digits 0, 1, 6, 8, and 9 while ensuring the reversed and rotated version is different from the original. Understanding this pattern is crucial, as the problem is designed to test your ability to manipulate digits, search efficiently, and handle edge cases effectively. By demonstrating these skills, you'll show a solid grasp of both the problem and its underlying concepts. This problem has strong ties to other LeetCode problems that explore similar concepts. For instance, LeetCode 248, strobogrammatic number 3, focuses on numbers that remain the same when rotated, offering a complementary perspective to confusing numbers. LeetCode 247, strobogrammatic number 2, narrows the focus to generating numbers of a specific length that are strobogrammatic. Another closely related problem is LeetCode 788, rotated digits, which also involves counting numbers that qualify as confusing numbers under specific conditions. Finally, LeetCode 43, multiply strings, is worth exploring because it tests your ability to manipulate numbers and strings, a skill that is highly relevant to solving problems like this one. Diving into these related problems can help you build a deeper understanding of number transformations and efficient computation techniques. There are several approaches you can take to solve this problem, each with its own trade-offs. A brute force approach involves iterating through all numbers from 1 to n, reversing and rotating each number to check if it qualifies as confusing. While this method is straightforward to implement, it becomes inefficient for large values of n, as it has a time complexity of O and *d, where d is the average number of digits. A more efficient approach is to generate valid numbers digit by digit, using recursive construction. By leveraging only the valid digits 0, 1, 6, 8, and 9, you can significantly reduce the search space. This method is faster but requires more careful implementation. Another option is to pre-compute a map of valid rotations, such as mapping 6 to 9 and 9 to 6, to speed up the validation process. However, this approach comes with the trade-off of increased memory usage for storing the map. Choosing the right approach depends on the problem constraints and the balance between time complexity and memory usage that best fits the scenario. Great job! In this problem, we explored the concept of confusing numbers and how to identify them using a brute force approach. We touched on key problem-solving strategies and takeaways that will help you tackle similar problems in the future. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!